Which of the following is the strongest acid? And so what we have here is we have a series of organic molecules. If we had pKa values, then we could easily see which is the strongest acid. But in this case, we do not have the pKa values, we have the structures. So we need to use these structures to evaluate the relative acidity. So we're going to use the trend that we have been using for a while now to evaluate acidity, and that is the cardio trend. So we'll write this out quickly. So C is for charge. That's what tells us, for instance, that protonated water with a positive charge is more acidic than neutral water. We don't see any charges here, so that's not going to come into play. Atom. So when we're comparing atom, we're looking at the atom that the acidic hydrogen is attached to. So that is often an electronegative atom. So if we look at all of these structures, we have hydrogens attached to the carbon backbone, and we have hydrogens attached to oxygen. So the hydrogens attached to the oxygen are going to be the most acidic in all cases. And since it's all oxygen, this A does not differentiate for us. So we will move down to R, which is resonance. And we see that A, C, and D are all carboxylic acids, and those all exhibit resonance. So only B has no resonance. B is an alcohol in terms of its functional group. A, C, and D are all carboxylic acids. And carboxylic acids are more acidic than alcohols because once we form the conjugate base is stabilized. So we have this sort of resonance when we have a carboxylic acid. So after we removed that acidic proton, then we have a negative charge on the oxygen, and that negative charge is actually shared between the two oxygens. So because they share that charge, that makes it more stabilized, which means that it is a weaker base, which corresponds to its conjugate acid being a stronger acid. Okay, and so we need a way to differentiate these carboxylic acids because they all exhibit the same resonance. So we're going to move it down our trend to the Di, which stands for dipole induction. And this is what's going to allow us to differentiate. Before I go back to that, though, I will fill in the O orbital, even though it does not come into play in this problem. Okay, so we're talking about dipole induction. This is the presence of another group in the molecule that could possibly help to pull some electron density away from the negative charge that you form in order to help to share the charge. So the two things that we look for when we're looking at dipole induction is we're looking at electronegativity. The more electronegative atom will have a greater effect. Okay, and so what we have for substituents here is we see that A and C both have a chlorines. They both have dipole induction. So C has resonance, but it has no additional dipole induction. And so the more electronegative the atom it is, the greater effect it will have. In this case, we see that they are both chlorine. So that's not changing things. The other thing we need to consider is also proximity. So the closer in proximity to your acidic hydrogen that electronegative atom is, the greater of an effect it has. So we can see here it's on the next carbon. On D, it's right next to that carboxylic acid. And on A, it's 2 carbon atoms away. And so that's what makes D these stronger acids. So it has resonance. And then in terms of dipole induction, the chlorine is closer to the acidic hydrogen. which means that it can pull more on the electron density of that anion once it's formed.